The fundamental theorem of calculus basically ties integrals and derivatives together, namely that integrals and derivatives are inverse operations, the way adding 3 and subtracting 3 are inverse operations, the same way that squaring and taking a square root are inverse operations. I think squaring and taking a square root, maybe that is a better analogy. Because even though squaring and square root are inverse operations, you don't always get exactly what you start with. What do I mean by that? Well, let's say you square something and take the square root, or you take the square root and then square whatever you got. Well, in one of those cases, you always get exactly what you start with. But in the other case, when you're squaring something and then taking the square root, you don't always get exactly what you start with. You just get mostly what you start with. You actually get the positive version of what you start with. Anyways, the fundamental theorem of calculus is usually talked about in two parts. The part we're going to do today is what's typically called part 1. So, by the end of this, hopefully you can evaluate some definite integrals. So, if f is continuous on a closed interval a to b and differentiable on an open interval a to b, then the definite integral from a to b of lowercase f of x dx is capital F of b, or capital F evaluated at the upper bound of integration, minus capital F of a, or capital F evaluated at the lower bound of integration. Don't confuse lower and upper bound with larger and smaller. Sometimes we're going right to left, not always left to right. Anyways, it says where f, capital F, is an antiderivative of lowercase f. Super important. This says an antiderivative. There are lots of antiderivatives. That's what that plus c thing is about, that you write when you're doing indefinite integrals, but we'll get to that in a moment. So, can you put that thing into your own words? That if f is continuous on the closed interval a to b and differentiable on the open interval a to b, then the definite integral of f of x dx is capital F of b minus capital F of a, where f is an antiderivative of f. So pause the video right here and try to put that into your own words. I don't know, write it down or say whatever you were going to say out loud. Did you pause? Did you write something down? Okay. If we can put this into shortest terms, here's what I would say. To evaluate a definite integral, subtract the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. Isn't that what this basically says? To evaluate a definite integral, subtract the antiderivative evaluated at the upper bound minus the antiderivative evaluated at the lower bound. That's probably not as precise as we want, but the goal here was putting things into your own words, so you're trying to internalize these ideas. Okay, so we're going to evaluate some definite integrals using this idea, this fundamental theorem of calculus, and we're going to show all our work. You're going to use your graphing calculator to verify your results. I'm not. I'm on a touchscreen tablet, and in all honesty, I probably should have used Desmos or something to make these graphs, but I'm going to leave that up to you. So how do we read this? The definite integral from -1 to 2 of 2x minus x squared dx. Well, maybe we can kind of sketch to see what we're supposed to get. So let's see. Y is equal to, let's see, we can factor out an x and 2 minus x. So we're trying to draw a parabola that has a root at 0, a root at 2, opens downwards. Something like this. And we're finding, we're going to get some negative area plus some positive area. But when we're doing that definite integral, we don't really have to worry about those negatives and positives. That's just going to happen automatically. All right. Well, by the way, when it says graphing calculator, in this case, it actually doesn't mean to graph. You need to use FNINT which is if you're using an 83 or an 84 under the math menu. If you have the pretty print version, it's pretty easy. If you have the 83, you're going to put in your function, and then you're going to put in x, and then you're going to put in lower bound, and then you're going to put in upper bound. This x refers to this dx. Right? That's finding the antiderivative with respect to x. So you could use, like in another case, t below. Okay, so show all work. So if we're going to evaluate a definite integral, we need to find an antiderivative. What has the derivative 2x? X squared. What has the derivative of x squared? Well, not x cubed, because the derivative of x cubed would be 3x squared. So x cubed over 3. I recommend, if you're in my class, I'll make you do it, putting brackets around this whole antiderivative. And also, not just writing -1 down here, but writing x equals -1. That's going to matter when you change variables, maybe do use substitution. Okay, so that's the first thing, antiderivative, and we're going to evaluate from x equals -1 to x equals 2. And then I like to keep structure in here, so 2 squared minus 2 cubed over 3 minus -1 squared minus -1 cubed over 3. We'll just evaluate a little bit here, and we're going to have 4 minus 8/3 minus 1, and then that's going to end up being plus 1/3. Right? Minus a -1/3. -1 cubed is -1. With that negative is positive, but kind of with this little negative is going to be negative overall. So 4 minus 1 is 3, and -8/3 minus 1/3 is -9/3. 0. Hopefully that's correct. I don't know. I guess that kind of makes sense. I didn't really draw my graph to scale, but we're going to get a lot of vertical movement down to -1. Maybe I will grab my graphing calculator to check. You just won't be able to see it. I'm going to pause, so it's going to seem like I did this instantly. So my calculator said -1.5 e to the -14, which is, I mean, it's engineering notation, but that's the same as -1.5 times 10 to the power -14, so that's -0.0000. It's pretty much 0. Remember, your graphing calculator is not magic, so that kind of synced up. Some of you might be wondering why we don't need to write a constant of integration, meaning that plus c, when we're evaluating a definite integral. So let's think about this. Well, what would have happened if we did add that plus c? Well, let's do exactly what we had before. So we had x squared minus x cubed over 3, and now we're going to write, I'll do it in a different color so it pops out, plus a constant. Let's see what happens. So I'm still going to evaluate from x equals -1 to x equals 2. And remember, that plus c could be 1 or 2 or 5 or 10. Because no matter what that c is, when we take the derivative of x squared, we get 2x. When we take the derivative of minus x cubed over 3, we're going to end up with minus x squared. And the derivative of 2 is 0. The derivative of 10 is 0. No matter what this constant is, it will have a derivative of 0. Okay, so let's continue working. So just like we did before, 2 squared minus 2 cubed over 3 plus constant minus -1 squared minus -1 cubed over 3, and then plus the same constant. Right? No matter what, those two blue C's have the same value. We don't know what that constant is, but we do know those two C's have the same value. So maybe we do this like we did before. 4 minus 8/3 plus that C, and then we're going to have what? -1 minus 9/3 minus C. So those C's always subtract out, which is why we don't need to write them, why we typically don't write that plus C. maybe a better answer for that, why don't we write the plus c, is because a definite integral actually gives you a change in a function more than it gives you area under a curve. So the area under 2x minus x squared from -1 to 2 is actually also the change in y of this x squared minus x cubed over 3. That's actually a little bit easier to understand when we're doing position, velocity, acceleration stuff. Okay, so what about the definite integral from 1 to 4 of 2x plus 3 over x squared dx? Well, hopefully your eyes are already drawn to this x squared. 2x plus 3 over x squared isn't continuous everywhere. Definitely not continuous at x equals 0. Definitely not differentiable at x equals 0. But is continuous and differentiable everywhere on 1 to 4. So we don't really have to worry about that stuff. All right. So how in the heck are we going to find some antiderivatives here? Because here in my class right now, we haven't done substitution. We haven't done integration big parts. We haven't done anything except like relatively easy antiderivatives. So what I would recommend doing, and I'm just going to move over to the right so I have a little bit more room to work. I'm going to rewrite this as the definite integral from 1 to 4 of 2x over x is 2 over x, right? I'm just going to split this into pieces. Plus 3 over x squared all dx. Don't forget those parentheses. Don't forget a definite integral is adding up the area of infinitely many rectangles. This first piece is the height of each rectangle, or a formula to find the height of those rectangles. And the dx is an infinitesimally small width. So width times height, width times height, width times height. If you didn't have these parentheses, I guess you're not really multiplying that width times the whole height. We know what you mean, but a little clearer here. So maybe I'll go ahead and rewrite this as 2 to the power negative x plus 3 to the power negative x squared dx, because by now hopefully you know that the power rule does work for negative exponents. So let's see. I know what people are going to get wrong here. They're going to try to add 1 to the exponent -1 and then divide, but that would give you 2 times x to the 0, I guess, divided by 0, which doesn't work. Don't forget, what has the derivative of 1 over x? Natural log. And we do need absolute values since, well, maybe not in this case. I was going to say we do need absolute value because it's allowed x to be negative, but for the x's we are using, namely all the x's in between 1 and 4, we don't necessarily need that absolute value. Okay, so what has the derivative of, let's see, 3x to the negative second? Well, it's definitely going to be x to the negative first, and definitely not going to be 3. Or is it? Oh yeah, just a negative 3, because if I did the derivative of negative 3x to the negative first, that would be negative 3 times negative 1, x to the power negative 2, which is going to be 3x to the negative 2, or 3 over x squared. Okay, perfect. That's what I want. Okay. And then we don't need the plus c. We're going to evaluate from x equals 1 to x equals 4. So 2 natural log of 4 minus 3, I'm just going to write it in this other form, over 4, minus 2 natural log of 1 minus 3 over 1. So without a calculator, who the heck knows what we're going to do? I would assume this is going to end up saying natural log of 16. Remember, you can take the coefficient to a logarithm, make it an exponent, so minus 3/4 minus natural log of 1. Don't forget that 1 squared, if we do kind of that same thing, we're good to go. But natural log of 1 is 0, so that's going to disappear anyways, no matter how you slice it. And so I guess the best we can do is natural log of 16 minus, let's see, 12/4 minus 3 more fourths is minus 15/4. All right. Little bit harder things. Well, I think most people know an antiderivative for cosine. What's an antiderivative for exponential functions like e to the x? Well, let's do a quick review. Most people know that the derivative of e to the x is e to the x. I like to say the derivative of e to the x is e to the x natural log e. Now, natural log of e is 1. But if you get in that habit, then every time the derivative of e to the x is e to the x natural log e, then you can say, hey, the derivative of 2 to the x is 2 to the x natural log of 2. Okay. And so we're thinking ahead here. What's an antiderivative of 2 to the x? So let's say y equals 2 to the x. We don't want to say y. Maybe we say g. So that way we can say capital G. That means g of x would be, well, it involves 2 to the x, but if I did a derivative, I'd have to multiply by natural log of 2. So I divide by natural log of 2. Let's see, what's g prime of x? Well, that's obviously g of x, which is also 2 to the x over or maybe we just ignore the natural log of 2 in the denominator. Let's start there. Natural log of 2 is a constant. So the derivative of 2 to the x is 2 to the x, natural log of the base 2, and that does end up with 2 to the x. Okay, cool. No joke, those are the sort of things I'm doing in my head all of the time. If you know where things come from and why they happen, you don't have to memorize all that much. Now, I normally wouldn't write all of that, so things would go more quickly. Okay, so the antiderivative of 2 to the x is 2 to the x over natural log of 2. Oh, shoot. Is the antiderivative of cosine negative sine or positive sine? Positive sine of x. I probably should have said, hey, 2 to the x is continuous everywhere. We don't really have to worry about continuity or differentiability. Cosine is continuous everywhere. We don't have to worry about continuity or differentiability. So let's see. 2 to the pi over natural log of 2 minus sine of pi. Let's see, minus 2 to the power 0 over natural log of 2 plus sine of 0. Hey, I might as well simplify since sine of pi and sine of 0 are both 0. Dang, 2 to the pi I can't really simplify. So I guess I'm just going to leave this as 2 to the power pi over natural log of 2. And then minus 0 minus 1 over natural log of 2 plus 0. I suppose I could combine. Maybe that's what we're expected to do. 2 to the pi minus 1 all over natural log of 2. But at that point, you know, who cares? Can you do this same sort of stuff from a table? Well, I don't think that's terribly hard, but maybe it's different. How are we going to do the definite integral from -1 to 3 of f prime of x dx? Well, don't forget, to evaluate a definite integral, we're going to do the antiderivative. What's the antiderivative of f prime? F of x. Evaluated from x equals -3 to x equals 1. So that's going to be f of 1 minus f of -3. That's actually really easy, but might seem really hard. So going back up to the table, let's see. F of 1 is -2. Minus f of 3 is 1. So we end up with -3. I don't think that's that bad. Ooh, a little bit more complicated, but not that bad. So what do we do with the 1/2? Well, constant multipliers, we don't care. So the definite integral from -3 to 3 of 1/2 f prime of x plus 2f double prime of x dx. So let's work on some antiderivatives. Just the antiderivative of half of a function is half of the antiderivative. So 1/2, antiderivative of f of x. And the antiderivative of 2f double prime is 2f prime. Okay, I don't think that's that bad. From x equals -3 to x equals 3. So 1/2 f of 3 plus 2f prime of 3 minus 1/2 f of -3 plus 2f prime of negative 3. If you're thinking you can skip this line of work and you're going to take College Board's AP test, you're wrong. They're expecting you to show what you're substituting for. Once you write this line, you can do everything else in your head if you want. I don't think that's probably a wise idea, but, you know, who knows. Okay, so 1/2 f of 3 is 1/2 of 1. 2f prime of 3, let's see, f prime of 3 is 3, so 2 times 3 minus, and then I'm going to keep my brackets. I know I always screw up subtracting a negative. 1/2 f of negative 3, f of negative 3 is 4, and 2f prime of negative 3, f prime of negative 3 is negative 2. Bonus time, don't forget, AP test. You don't have to simplify addition, subtraction, multiplication, or division, no matter how long, hard, or easy things are. So I'm going to stop right there. All right. How do we find the equation of a tangent line of f at x equals 3? It's actually not that bad. Tangent line to f at 3 is going to be y minus f of 3, which is going to be, what's the slope? F prime of 3 times x minus the x value, 3. I'm going to rearrange. I'm going to bring this f of 3 to the right-hand side since I know we're going to approximate 3.1. So let's see. Y is equal to, what's f of 3? F of 3 is 1 plus f prime of 3 is 3 times x minus 3. So now we can say f of 3.1 is approximately, because by the way, this is, it's not f. This is approximately f because we're using a tangent line. We don't know exactly what f looks like, but we, I guess, assume f is, f is at least differentiable at 3. We have f prime at 3. Okay, so f of 3.1 is going to be 1 plus, well, now we just put 3.1 in it. 3 times 3.1 minus 3. F of 3.1 is about 1 plus, and that's 0.3, 1.3. And so notice, I really don't have to label, hey, what I'm doing. It told me to approximate f of 3.1, so I just wrote f of 3.1 is approximately. I might have had to do some more writing if I didn't do this y equals over here, because then it should be obvious, hey, the 1, the 3 are all the same.